Hey everybody, thank you for joining us today. So we're here to talk again about AWS RoboMaker. I'm Alejandra and I work here in AWS Developer Relations, and I have two awesome guests with me today. I have Ross and I have Cameron, and I'm going to let them introduce themselves.
Hi, I'm Cameron. I'm an AWS RoboMaker developer.
And I'm Ross. I'm also an AWS RoboMaker developer.
So we were just talking a moment ago about how we all got into curiosity related to robots, or how some folks got into robotic development. And I was dying to know, hey, Cameron, how about we start with you? How did you get into robotic development?
It was just interest from when I was a little kid, and going into college, I studied robotics, and I never got bored of it. So here I am doing some more of it.
And what was one of the first things that you remember got your interest?
I remember tearing up all of my electronic toys and soldering them together in weird ways, and that was
Ooh, Chucky, okay. Well then, hopefully a little bit less scary story from you, Ross. How did you get interested in robotics?
Yeah, I guess mine was a little bit later on in life. I was learning a trade in high school and then decided that I wanted to try and make my electronics project be a little bit more robotics. So I decided I was going to make a hand that moved when my hand did, just like kind of watching some of the superheroes. And I managed to make one finger move most of the way my hand would as well. And I thought that was awesome, so kind of went into it. I'm also destined to do robotics because my name is Ross and robot operating system, so
And
really
Ross
a choice.
is like, did your parents know this when they named you this, you think?
Oh, I definitely think so. They had to.
It's in the stars. All right. Well, as you can see, we have the best cast here to talk about robotics today. So let's go ahead and get started. So what are we building today?
Sure. So let's cue back to the screen and let's take a look at a quick simulation so we can see what's actually what we're going to be looking at today. So I'm just going to do, I'm just going to go ahead and launch the system that we already have running from AWS RoboMaker. And so where I get all this and we'll start in a minute. We'll go ahead and launch the simulation, launch Gazebo on my local machine so that we can see what's happening, and then we'll go into it a little bit. So here's our little room, and what our goal is for today is to have two robots be working around in this little flat, so two little robot roommates, and they'll be able to navigate around the apartment and even know where each other are. So getting an understanding of what we need, try imagining this. You left your wallet in your office and you have a coworker that works in a different building and wants to go check it out. And you say, well, do you mind picking up my wallet while you're at the new office? And they said, sure, why not? Well, how do I describe where my wallet is to my coworker? How do they know and walk around just to go and find it? And especially if you hit it in a very difficult place.
Which hopefully you would with a wallet.
Right. And how do you prevent them from spending hours looking for your wallet? So that's kind of how we're trying to relate these two robots.
Awesome. Okay. So would we also get to learn a little bit about different techniques related to localization and mapping?
Yeah, so the whole goal for this one is that we're going to have two robots, one which does all the scouting and actual mapping, the other which learns how to localize inside of that map, and then both of them being able to drive around together.
Okay. Well, it sounds like we have a lot of little problems to solve all at once. Where do we even start?
So if you notice here, we have a blank room. We have no robots inside of here. So first we need to get those two robots inside of this world. And then next we need to configure each robot to understand its location in relation to the other.
So then we need to find and configure the mapping and localization processes of each robot. And finally, we need a path planner for each of the robots to start driving them around.
That makes sense. Okay, can we do this with AWS RoboMaker?
So we can definitely do this with AWS RoboMaker. Everything that we're doing is open source and using existing open source ROS packages.
Okay, just out of curiosity, if some folks in the audience wanted to check those out, is there a good link to shoot them out?
Sure, yeah. So one thing that we're going to be using today is we're going to actually be using some of the code from AWS RoboMaker's sample application. So if you go to AWS RoboMaker and you scroll down, you'll see the navigation and person recognition. So what we're going to be using is building on top of this code to allow two different robots to understand where each other are. And maybe in your own time, if you get through this Twitch stream, you'll be able to have them do coordinated person recognition.
Oh my God. Yeah, so if you guys want to check this out afterward, just go to the basic homepage of AWS RoboMaker documentation, and we have links to all of the GitHub that have full cloud extensions, so you guys can grab these, download them, and just play around with them yourselves. All right, cool. So I think that the first thing we need to worry about is setting up our environment, right?
Sure.
So usually you have to worry as a robotic developer with setting up an Ubuntu development environment. And for anyone who's ever worked with setting up a development environment of any type, you know that that can be anything between minutes to hours to days, right? It just depends on how lucky you're feeling or being that day. What about us today? Do we need to worry about that, or is there something else we can do?
So for today's demonstration, we'll be doing it on my local laptop. So it does take some setup, but most of this can be done, or all of it can be done in AWS RoboMaker as well, which is already equipped and ready to handle this simulation.
And what you mean by that is the RoboMaker IDE that we have currently up for the audience, right?
Correct.
All right, awesome.
And so on my machine, I'm running 1804 Ubuntu with a Docker image on top running 1604 for ROS Kinetic. We'll be using Gazebo 7, so you would have to set that up. Normally for these type of systems, we'll go onto Docker Hub, go onto ROS, and grab the latest ROS Kinetic release or ROS Kinetic and build on top of that.
Okay, awesome. So let's go ahead and start thinking about how we're going to configure all these different robots. You know, where do we start?
Yeah, so that's a great question. So after pulling down the navigation and person recognition sample application, if we look on my screen, we can go to the person detection simulation underneath simulation workspace, source, and the person detection simulation. And we're just going to open up the smallhouse.launch file. Now, this is the file that is used for the person detection to actually launch us into that simulation that we saw earlier, except this one has no robots. If we notice here, we see that the world gets launched here, which is the one that I launched manually by hand. And then there's also this spawn robot right here. And this allows us to actually launch the robot into a certain location inside of this simulation. So let's go ahead and make this part happen. So
just out of curiosity, and I don't know if anybody else in the audience is wondering, why is it called Spawn Robot?
Yeah.
Why is it such a fun name?
Do you want to?
Well, geez, I guess Spawn is kind of like a video game concept as well.
Okay.
But it's like, where do you actually make it appear in the world, or just come into existence? So spawning just makes it be there.
Yeah.
It's spawned. All right,
spawned.
awesome. Okay, cool.
So let's go ahead and we can actually run this exact script from my local simulation so that we can iterate really quickly. So this is going to be under person detection simulation and smallhouse.launch. So the first thing we'll do is we're going to go ahead and remove these for now and let this simulation end. And so I actually have the person detection checked out right on my local machine so that I could develop really, really quickly.
So the person detection app that's ready in the RoboMaker documentation, like you just checked it out already, and that's the one that we're using.
Exactly.
Awesome.
And so I just went into my simulation workspace where I will then do a build and let it build by itself. Now, there's a few bits of magic that we've done in order to get to this situation or get to this point inside of here that RoboMaker does for you. And so really quickly, we're going to look at a source file that I've created. And this allows me to set up all of my paths that I need in order to run Gazebo, run all the robot workspace, all the simulation workspace, and source Kinetic. So if you just take a quick look, this is all on wiki.ros.org, but I've condensed it into a single file to allow myself to iterate really quickly.
And for folks watching along, we'll go ahead and drop that link in the chat box for you.
Exactly. So let's go ahead out of there. We're going to head into the simulation workspace where we would then go ahead and build. So we're going to go ahead and run colcon build here. And it's going to go ahead and build AWS RoboMaker and a couple of other pieces. And so now we want to launch with a single robot. So if we look here inside of RoboMaker, we see that the spawn robot is hopefully going to spawn a robot at the X position 3.5, assuming in meters, and Y position 1.0.
So I noticed that you're not choosing just a default of 0, 0. And why is that? Because we discovered something fun happens then, huh?
That's a fantastic question. Actually, we'll go ahead and launch the robot now and we can take a look.
Okay.
So we're going to have to run the ROS launch command with person detection simulation and smallhouse.launch. So we'll go ahead and do that now. So ROS launch, person detection simulation, smallhouse.launch, and hopefully once that starts running, I'm going to have to put this one in the background and pull up GZ clients, which allows me to go ahead and visualize it. So a lot of times when we're working with robotics, we'll run Gazebo in the background instead of actually being able to look at it. The reason we do this is once we actually have our system knowingly and working, we'll mostly be verifying a lot of the other node configurations that we have. So let's take a look here and hopefully, there's our little robot. Luckily, right at 3.5 and 1. Now, if we put this at 0, 0, we may actually just see that this robot gets teleported into the couch, which is not a great place for the robot to try and escape from.
Yeah, no.
So we actually move the robot right over here. So let's move on to getting the next step.
Okay.
So in this step, we're going to need to actually launch the 2 robots. But before we get there, we need to understand how we are going to have these 2 robots in here. So there's 2 pretty interesting pieces that you need to understand, which are the node that actually runs is running a robot publisher state. So what's happening is, if we were to go ahead, I'm going to move over to my toolkit. So we're going to open up RQT, so ROS QT tools. And we're actually going to see a couple different things. So if you look on the right side here, we have this robot state publisher and this joint state publisher. And what this is actually doing, and we're going to go over this a little bit more in detail, is publishing where the robot thinks it is relative to its wheels. So where is, in my case, it's where are my feet relative to my hands, and vice versa. So this is publishing all of that. And Gazebo is giving it the publish of where it actually is inside of the room. If we look,
that's the point that we just put in there, right? The
exactly.
3 dot whatever. Okay.
Exactly. And so we look on the left-hand side, we see this is called the transform tree. And notice how all of these have its ODOM, base footprint, base length. All of these are really important pieces to our system. But what we need to know is that this is only for one robot. Mm-hmm. And so if we add another robot, we're going to have collisions. There's going to be 2 ODOMs. There's going to be 2 base footprints, 2 base lengths. There's going to be 2 robot state publishers.
Right.
So we're going to have to make a plan on how this is actually going to work. And luckily, ROS has done this pretty well for us as far as making these things called reps, which allow us to look at how this robot is supposed to be configured in order to have multiple robots. So if we take a look at this rep, this one is called coordinate frames for mobile platforms. And if we scroll down, we're going to notice something really interesting as we get really close. So there are these relationships between frames, which goes from Earth to map to ODOM to baselink. And this has been standardized for all of ROS. So baselink will be the location underneath the robot on the ground plane.
Okay.
So, and if we had a multi-robot situation, we would have Earth, then we have map 1 and map 2, and ODOM 1 and ODOM 2, and baselink 1 and baselink 2. And if we notice, that's quite a bit of manual configuration that we have to do for each of these frames. We'd have to write an XML tag for each one. Mm-hmm. So now that we're looking at our system, we see robot state publisher 1 and 2. We're going to want to go ahead and make some modifications. So now's the time where we're actually going to get to code. And our goal is to go from the situation that we have now in RQT, where it says ODOM and joint state publisher, to having some sort of identifier on each one so that we know which robot that we're talking about.
I really liked how you explained that. Thank you.
Sweet.
All right, cool.
So let's go ahead and we're going to just get out of all of what we have going on so we can start clear. So let me go ahead and get rid of that. So what I've done prior to going on Twitch stream is taking a look at RoboMaker, taking a look at this Twitch stream, taking a look at this person detection simulation, and all I've done was actually copied this entire folder over to a new one called MultiRobot Simulation. Now, normally I would just either edit it or rename or start moving around, but for simplicity's sake, and if I ever break anything, I have something to go back to.
So I have a question on the directory structure.
Sure.
I know that usually you need to worry about the robotic workspace as well as the simulation workspace. In today's demo, are we only working on the simulation workspace?
That's a great question. So today's demo is going to do both. So normally we split it up in such a way that if I were to ever run on the robot, only stuff that gets created in the robot workspace goes onto the robot.
Okay.
And nothing in simulation workspace should ever affect
Right.
what happens to the actual robot. So all the code that we're going to do now to getting the two robots up and configured properly are going to go in simulation workspace. Because in the real world, we'll have two robots that also have these same configuration properties.
Okay. Awesome.
Super sweet. So what I've done is I've copied over, I did CP for person detection simulation, and I created this new one called MultiRobot Simulation. So we're going to go ahead into MultiRobot Simulation and take a quick look around, quick peek. Now, notice that this looks identical to the person detection simulation. So all I've done was copy. The things that I have changed was going into the package XML. I've changed all the names to have MultiRobot Simulation so that we could have the same system. But otherwise, it's identical.
And the next thing we would need to worry about would be creating the launch file for this one, right?
Yes, exactly. So now what we're going to do is actually edit this launch file to get the configuration that we want. So let's go ahead into this launch file. I'm going to go ahead and copy the person detection simulation launch file over. And I'm going to go ahead and take a look at what is inside of here now. So notice we have this spawn robot location. We have, we're going to go ahead and spawn this robot.launch, but we don't have any identifiers. So there's two different identifiers that we need. If we looked at that RQT graph, we saw one which was the transform identifier and one which was the node identifier. And there's two ways to do that. So one is called namespacing. So when we namespace something, we are basically adding a prefix to everything that we launch underneath it.
Okay.
So let's go ahead and do that now. And our goal is to see what actually happens to our system. So first thing I'm going to do is I'm going to need to group a namespace, and we're going to call this one just TurtleBot1. I'm not particularly good at...
I like how you said TurtleBot1 and then you named it TurtleBot2 for
I
a second.
did, yeah. I just got excited. That's cool. I was like, let's go ahead and get two in here. So, boom. So now we have TurtleBot1, and I didn't escape this one. Sweet. And that should be all I wanted there. And then there's two other pieces to this. So something that happens when you're using two robots together, and I'm also using the TurtleBot3 description reduced match. All of these launch files came from open source. Well, when we're doing things like this, there are sometimes hard-coded files inside of those that need new parameters. In this case, I've actually had to go ahead and modify and add two new parameters to allow this system to work properly. So the first one is we're going to need an arg, and the name is going to be called, we're going to call it RoboRobot namespace. This is something that is used in the URDF default equals TurtleBot1, and I could have done this with an arg, but I am a little slower today. And then the next thing is the model name. So what I've done is I've changed the model name, which used to just mean which model it was going to be, such as Waffle or Raspberry Pi or any of those. And I've changed it to actually just mean what we want to call the robot. So what's the robot's name? It'll allow us to override some of the properties later. So we're also going to call this one TurtleBot1. Sweet. And so that'll give us the namespace. So let's go ahead and take a look at what actually happens now. So I'm going to CD back to my workspace, and I'm going to Qualcomm build again.
And just out of curiosity, when you're thinking about best practices, how often do you as a developer find yourself running Qualcomm build? Like when would be a normal time to do that?
That's a good question. So anytime I touch any files inside of my system, I have either an auto build script if I'm running on my own local environment, or I just completely rebuild every single time by manually. And this is to prevent, first of all, accidental edits of install directory files.
Okay, gotcha.
Which can happen when you're developing. So just be careful, where you are in your system. And then also just to make sure that I didn't accidentally introduce a bug a while ago and just Qualcomm build now and found out.
That's true.
That can be.
So it sounds like you're running Qualcomm build quite a few times during the day.
Yeah, quite a few times. So now I'm going to go ahead and ROS launch, and we should see MultiRobot Simulation show up, which we do, and we should see a smallhouse.launch show up. Now, because we're doing this live, I really hope that this works. So we're going to go ahead, and it looks like it did launch. If we see here, I'll actually scroll up just before we get too far down the logs. Notice that process has changed. Now we have TurtleBot1 / So this is a pretty cool hint to know that we're on the right track. So let's go back to our tools page. And we should see over here, look at this. We have this grouping of Turtlebot 1 around the joint state publisher and the robot state publisher. So we're on the right track. So we have one robot in. We know that this is all set up. But if we go down here, notice that base footprint isn't connected to the Turtlebot 1. So what I did was I added those namespacing extra tags in there, and now they're split. So I still have base footprint. All of the Turtlebot system is still the same way. So we need to fix that.
Yeah.
And how do we fix that? We're going to use something called a TF prefix. Just like we had with namespace, TF prefix is going to go and prepend any of your transforms that are being published.
So TF standing for transform.
Transform, perfect.
Okay.
And we're going to go over what those are and how those work in just a minute. So let's go ahead and get out of here, and we will leave Gazebo. And then our next thing we'll do is we're actually going to go ahead and edit that again. So let's head back into Source, MultiRobot Simulation, and Launch. And let's take a look at the smallhouse.launch again. So we had this grouping of a namespace. So we're going to go ahead and add the tag for, it's called a parameter TF prefix. So we're going to go ahead and call param name is equal to TF underscore prefix. And for simplicity's sake, I prefer to keep all of the prepended names to be identical. So if this is Turtlebot 1, the TF prefix should be identical to the namespace prefix. So whatever's grouping the entire robot, group that with the namespace. And then you can always differentiate between the two.
And hopefully make also the code easy to read for the next person.
Exactly.
So the next poor soul who comes along.
So once you'll see a pattern emerge as we continue, you'll see that we're going to be doing a lot of copying and pasting in this segment, but once you were actually going to go ahead and use this and continue and iterate, I would then refactor this to use a bunch of args and options to allow for this to happen properly. So notice how we put the param inside the grouping, so that way anything inside of this grouping has this parameter. So let's go ahead and relaunch this. Oh, almost caught myself.
Don't you have to Coke and build first?
I do. And we would have saw the same thing.
We just learned 5 seconds ago.
So now that our system's back up again, we're going to go ahead and take a look at RQT. And wow, our tree's back to connected.
Oh,
and all of our system now is prepended with Turtlebot 1, Odom, and the namespaces, all Turtlebot 1.
I gotta say that being able to also see the graph really helps you to better understand what it is that you're doing in your code.
Yeah, I'm a very visual learner, so this is absolutely huge to me. And so the next part is let's try getting Turtlebot 1 and Turtlebot 2 running, okay? So now we can kind of skip as you guys are getting more and more familiar with this.
It'll be a lot similar now, right? Because what you're mentioning about copy and pasting, it's like a lot of the same things, except that now you're going to do it under Turtlebot underscore 2.
Exactly.
Okay.
So we're going to go ahead and go back into here, and we're actually going to create a separate launch file for Turtlebot 2. And I know that's kind of weird for Ross, and why I would do this, but the real reason is that Gazebo has a little bit of trouble with the timing when you're going to spawn robots. So sometimes you'll get 2 robots and sometimes you'll just get 1. So I'm going to go ahead and manage that timing manually. Remember that Ross launch will not manage any timing.
Oh, okay.
So
That's good to
it'll
know.
try to launch all of them at exactly the same time, separate processes, off they go, which is fantastic. Except when you want to add delays or structure your system.
So are you saying that you have to manually do this every single time? Or is it just because for the purpose of a demo, it's the simplest way to go about this?
You would have to do it manually every single time, except you can always script kind of whatever you want, which
That's
is
true. Scripting to the rescue.
Which is amazing. So we actually have Turtlebot 2 here. All of this is just copy-pasted, and we just have Turtlebot 2 instead of Turtlebot 1. And then the only other difference is our X and Y position. I do not want to put the robot on top
One
of the
to
other
each
robot.
other.
So
That
I
sounds sane.
added 1 to the Y position.
It's
So
almost like we're
see
trying
it.
to be logical.
Almost.
Okay.
Yeah. We'll work on that though. All right, so now that we have this, we're going to actually need to go ahead and make that script that allows us to launch these 2 at the same time. So let's go ahead and go back to my workspace. And I added this bin folder here. So if we go ahead and into bin, there's only one file in here, and I just named it Run MultiRobot Simulation. So if we open Run MultiRobot Simulation, there's very few things in here. There's 3 things. So one is to actually run the one we were doing by hand a minute ago, which was MultiRobot Simulation. And I've made it so that all the logs go into a specific log folder called gazebo.log because they flood my system. The next thing I do is I actually sleep for 10 seconds. And this could be really just maybe 1 or 2, but I always like to be
What made
safe.
you pick 10 specifically?
10 was faster for both fingers to do 1 on one side, 0 on the other. Very
Okay.
quick.
I bet it works every time.
Yeah, it works every time.
I was going more for that kind of an answer.
It does work every time. And you can always minimize this, but the next thing I do
It's
is
okay,
actually...
Ross, we still accept you.
I'm so sorry. And the next thing we do is actually launch the second robot. So spawn turtlebot2.launch. And finally, we added this read here. And this just reads from the standard in from TTY. So when I'm actually running the system, it just waits on that line until I hit Control-C. And when I hit Control-C, it'll kill the rest of the system.
What's the dev TTY thing? Maybe think of talk to you soon, but I'm sure that's not what it is.
No, so it's listening to the user input.
Okay.
Right. So what I'm going to do is when I actually launch this, you'll notice that it's going to pause waiting for user input. And when I hit Control-C, it'll trigger and actually just end the system. And this is important because ROS launches multiple processes. Okay, so if you exit out of this immediately, you'll find they're all hiding in the background. And then you have to go and clean up their PIDs, so clean up their process index. So what I'll do now is I'm actually just going to go ahead and run that multi-robot simulation. And hopefully it'll work. We'll find out in just a minute.
If it works, we should see an update in our tree and node graph, right?
We should, yeah. So we should see Turtlebot 1 and Turtlebot 2. Notice down here we actually see a Turtlebot 2 here.
Okay.
And so that looks like it's good. And notice we don't see Turtlebot 1. And that was because I redirected all of the output to a file. So we can't actually see that right now.
Gotcha.
Also notice quickly that I have 3 different tabs. I normally use 3 or more tabs whenever I'm working on simulation in robotics. One tab strictly for simulation, one tab simply for robot changes, and one tab for tools. This
That's
way
smart.
I can
Okay.
move all my systems.
All right, so keep a note of that trick, those 3 tabs, because you're usually doing at least 3 things.
At least 3 things. And so now we have something that looks pretty cool. We have Turtlebot 1, and we have a carbon copy of that, which we now call Turtlebot 2. Exactly the same, except that they're now indexed on their names so that we can differentiate between the 2. And then if we look over here, we get this really, really far away map.
It keeps getting bigger and bigger.
And so we do have Turtlebot 2 on one side, this Turtlebot transform tree, and we actually indeed have Turtlebot 1 on the other side.
There it is.
But notice they're not connected yet, right?
Oh.
It seems they're...
It looked like they were from here, but no.
Right, yeah, there's just actually a little gap right here. So they actually still don't know where each other are, but at least we can differentiate between the 2. So now we have a really nice system that we can start actually coding with for navigation and other purposes. So
This brings us to transforms, right?
yes.
So earlier you guys were mentioning a transform, and we have actually been talking and using the word transform a lot, but what exactly does that mean and why do we need it?
I saved a definition over here for that, so we'll find that. Okay, got it. A transform is a mathematical function to relate one state in space to another. In the robotics case, we can narrow such a broad term to data, which represents a translation and rotation from one location to another.
Right. And so this translation and rotation basically allows us to go from one location in the robot and reference the other. So for example, when I have my water bottle way out here and I actually have to go ahead and grab that, I have to coordinate quite a bit. I have to coordinate the tips of my hand, my finger, all the way to there. And that means all of these joints need to move in succession, and they need to understand in the relationship between the tip of my finger and my eyes in order to make that connection, or in this case, also feel. So let's go ahead and take a look at what the robot thinks of itself. So in this case, we're just going to open up another tab. We'll put that one in the background. We're going to use RViz.
And we get to see the transforms this time for the Turtlebot.
Yeah, well, actually, we may not because I need to do one more thing in order to actually go ahead and see that. But in order to see at least one of them, we can go ahead and change this to one of the robots. So, what do we have here? We see that because we're looking at, let's see, I chose Turtlebot 1. If we look at the transform tree for Turtlebot 1, it starts at Odom and moves its way out, right? And so visually, we can actually see that. We can see Turtlebot Odom, and it's going to move its way as we get really close. There's going to be a lot here. Let's
There's
go
definitely
ahead
a
and-
lot going on here.
yeah, let's go ahead and scale this down a little bit and actually remove some of the frames from this tree. So let's remove some of the casters.
So all of this big bunched up white text is basically printing out the different frames that are there, and so it makes it kind of hard to visualize as you're looking at the actual
Right.
matrix
I
itself.
see some weird things like wheel left link. This is
Yeah.
where the wheel attaches.
Right, exactly.
Okay.
So let's go ahead and take a look. So the first thing that you're going to see is actually base link. So it goes to base link, and then we have base footprint, which goes on top of that one. And then if I'm going to remove some of these, and I can start putting any single one of these, and notice that they appear in relation to the base footprint. So let's take a look at the back caster. So this back caster actually is at the bottom of the Turtlebot in the very back. And so that's its location in relation to the very center point of the robot. And so we can actually see that in this visualization here where it goes from base link, goes from base footprint to base link. And let's see if we can find that caster. We see the right wheel link. There it is, the caster back wheel. Boom. And so this is how we can
And
understand
is that
and
one the
traverse
left
the
one, I
tree.
guess?
Yep,
Back left, I guess.
exactly.
The one right next to it.
Right.
Oh, cool.
And so another important piece is some of the sensors that we have on this. I'm not sure if we're going to head on into that right now, but these sensors, such as the IMU link and the base scan and the camera link, are all sensors on top of the Turtlebot. And these sensors allow us, and this relation to these sensors allow us to coordinate them and create like a sensor fused system where we can understand where this camera is in relationship to my base so that I can actually go ahead and either grab it or touch the water bottle.
So let's ask a couple of questions here that I'm kind of curious about that I've been holding off on. First of all, how can we access these transforms and how do we get to see how they're related? I think so far we've just been using the node graph, right?
Yeah.
But if they had never done this before, like how do they spin it up or how does that work?
So that's a great question. So TF2 automatically will spin up with ROS if you're depending on it and you're actually using some of the APIs, which is amazing because it turns out it's actually distributed. So distributed transform system.
Should we add it to our dependencies then?
Yes.
So we have access to
yes.
it? Okay, gotcha.
But otherwise, it just comes with. And so, how do you access them? In code, it's pretty simple. There's a really nice TF2 API. It just allows you to say, hey, get transform, and then you give it the length that you'd like the transform to. And they have to be in this tree-like structure. They cannot be a graph. It must be a tree. So there must be roots, and they must flow downward. In that way, we have to relate something by tracing our way back through the tree. So if I wanted to relate let's pick the IMU, so the inertial measurement unit, with the camera, then that means I need to trace my way back up the tree to the base link, and then I also need to trace my way from IMU to base link, and then I would do the inverse of one and multiply them together, and that will give you the relationship between that one to the other one.
It's so interesting. It's so different from, I don't know, my background was more front-end UI, and then working and looking at these things, I'm like, this is so different, it's so cool.
So what's really cool is that if you're familiar with gaming, this is fantastic because gaming does all of this and even more complex SKUs than what we do in the real world because the real world can't shrink as easily or grow as easily or skew as easily as gaming graphics can. And you're also projecting something from 2D to 3D. We're just using 3D. It becomes a little bit easier.
I was playing Toadette in Super Mario Kart. Does that count?
It does count. If you know the transform between her and the shell that's coming at you, you will be able to dodge it.
Nice. Okay, cool. Okay, so I have a couple of other questions that I'm wondering about, and
Sure.
I know that we've kind of already talked about some of these, but we've also mentioned AMCL,
Yes.
and how would we be able to explain that to the audience?
So AMCL itself is fairly straightforward, except for the math that goes in behind it can get really complex. So we'll go into that a little bit in the future, but maybe we switch a little bit to what AMCL is actually doing, which is localization and mapping. So
Right, because we do need to worry about some of these mapping and localization techniques.
Right, exactly.
Okay.
So let's go ahead and let's exit all of this, because now what we have the two robots, we've done the easy-ish part. So let's go ahead and cancel that, let it shut down. It does take a second. And let's go ahead and start looking at some of the navigation tasks. So if I go up into my Cloud9 desktop again and take a look at some of the robot workspace, go into source and take a look at some of the person detection robot, go into launch and person detection.launch. Awesome. Actually, it might be a little bit farther down. So the Turtlebot 3 already comes with a bunch of launch packages to do like move base, to do all of these different localizations and path planners. So all I've done is actually taken those and gone into my robot workspace, created a new package called MultiRobot. So I cd into MultiRobot, and I'll take a look. There's actually no code happening here. All I'm doing is, again, coordinating some launch files.
Okay.
So if I go into my launch files, we're going to take a look at this is the raw Turtlebot 3 navigation .launch file that comes with the Turtlebot 3 stack.
Okay.
There's a couple different things in here. So first we see that there is the Turtlebot 3 map server. It has this thing called AMCL, which you just touched on, we'll go over in a minute, and it has move base. So these three components, let's take a look. These three components here are what we're going to be focusing on to get these two robots to actually work. So mapping and localization. For you and I to go ahead into a room and actually understand where we are, when you walk into a new room, or maybe even to Disney World for me, I walk into Disney World and I look around, and if I were to walk maybe a mile down one of the other ways, I would have no idea where I am. Right. And we do that, and what we do is we look at maps to help us localize and figure out where we are. And so that's what this map server right here is doing, is it allows you to provide a map to the robots that can look up maybe where it is or where it is. But how do you even look up where you are on the map? Does it say you were right here?
Not always.
Not always, right? And so sometimes you have to look around for these distinctive features about what's going on in your world. And these distinctive features can all depend on your sensors. Now, if you're blind, you're not going to understand where you are the same way that if you're not. So we each make our own way of doing it. And so AMCL specializes in geometric features. Mm-hmm. So, and what it does is it just basically uses a LiDAR to hit different points. So instead of seeing in 3D, you see in 2D, just a 2D plane, or maybe 3D and you squish it. And then you try to line it up with the current map that you're in. Okay. And so as you get closer and closer to the location of where you think you are, your probability of where you are or how much those actually match goes up. And so AMCL does a lot of other things. We'll actually go over some of the cool pieces, but that is the fundamentals of basic localization. Okay. And then there's also the part about mapping. What if you don't have a map, and you need to localize? So this is a really tough problem, and you have to
build your own map.
You have to build your own map while you're also localizing in that map. And there's a lot of really tough things there. And so we're going to be using for this non-commercial purpose, we'll be using Gmapping on one of the robots in order to figure out, do the localization and mapping at the same time, and AMCL on the other to localize within that map.
Okay.
I don't know if that was a little too much, and we'll go over that in a minute.
I think that made sense.
Perfect. Yeah. And then the next thing is we need to add a planner. So we have this move base.launch down here at the bottom, and that's in Turtlebot 3 navigation stack. And we're going to just copy and paste all this stuff over so that we can take a look at what's actually going on in here.
Oh, we're real developers.
Yeah.
We're so good at copy and pasting.
So a couple of things we need to do. We need to remember that there's two different namespaces. We need to remember that there's Turtlebot 1 and Turtlebot 2. And this is important as we decide which one is going to be the mapper and which one's going to be the follower. Okay. So let's take a look at this group right here. Boom. No. So down to here. Perfect. So this group in this namespace is Turtlebot 1, and it has the same TF prefix that we had before. So we just have the exact same setup as we did in simulation. And then we have move base in the very beginning here. So we're actually just going to launch exactly the same way as we did prior, and as Turtlebot has done in Turtlebot 3 navigation. But we're going to add a couple different things. One is we're going to change the command velocity topic. We're going to change that to be Turtlebot 1/command velocity. We're going to do the same for the odom topic, so the odometry from the robot. And we're going to tell it that it can move backward and forward because because we'll pretend that there's not enough friction to be an issue here. And we're going to say that the base link is actually the Turtlebot 1 base link. So we've just configured our move base to just use the transform tree that we expect.
Okay.
Do you guys have any questions?
Not right now. I think that makes sense to me.
Yeah,
For
I
now.
think so far. When you say that you're going to change it, like, do not just move forward, I notice that it says move _forward _only. So are you going to add another one that says move backward only? No, move backward and not only, I mean.
Yeah, so in this case, all it's trying to say is that whether or not it can have the option to move back. And this is important because you may not think, but in robotics, you have a caster on the back and you have the 2 wheels on the front. The caster is inherently smaller than the 2 wheels.
What's a caster?
The caster is a little free-rolling ball or a single wheel that has the ability to pivot, and it's non-driven most of the time. And the issue with that is it comes with some friction that can happen when you're trying to move in the direction of the caster itself. And so if I'm on something like this floor here is kind of carpeted, if I'm on a carpeted floor and I try to move backward instead of pulling, I might be pushing into something that has too much friction rather than dragging it along. And so you can have some issues with that as well. So by setting it to move forward only, we avoid those, and it can also become a little bit more predictable because our system is going to try to make these path plans all the time. And in this case, it's either opportunistic or immediate. And so what will happen there is if it's only going forward, then we know that it will only move forward. So maybe it's a big robot that weighs 300 pounds.
Yes.
You don't want it to go backward when you're not expecting it to go backward.
Smash forward.
Right.
I'm kind of visualizing like like when you see those little coffee cups that you get at McDonald's to say caution, liquid might be warm, and you're like, well, duh, but it's there because somebody made that mistake, right? So I'm envisioning, okay, let's add this argument of move forward only because somebody must have moved backward, crashed, broken everything, and then moved forward.
I actually had another question. We keep using the word odometry, and that's actually something I didn't understand what it meant for a long time.
Yeah.
Can you tell me what that means?
Yeah, so odometry is the understanding of where the robot is strictly based on what the immediate sensors on the robot are. So non-feature system. So this could be anything like your wheels have something like an encoder on it. And so they can try to figure out how far away it is. Now, for example, let's say that you close your eyes and you take 3 steps forward. You have some semblance of where you are based on those 3 steps in your normal gait.
Right.
Just like that, the robot has a very set size circumference of the wheel. And so if I can measure how many times I've rotated, then I can have some semblance of where I am. And that works really well, except for when maybe there's some slip involved. Maybe it's like you slide a little bit or there's a lot of friction. So it's trying to overcome that. And then the other thing that can actually happen with odometry is you can do visual odometry, and it's where it tries to figure out what its odometry would have been from the wheels based on both what you commanded the wheel and what you're seeing around you. So something like a tracking mouse, like your mouse that's on your that's attached to your computer, is also doing visual odometry. It's taking pictures and lining up and trying to figure out its velocity.
Oh, I hadn't thought about the trackpad.
Okay.
That's so interesting.
So that's what this odometry topic is.
Okay.
What about down there where it says TF_map_scan match? Transform frame name.
Let's see, which one was that? Oh, so this is under Hector Slam. So I have two slams here. We're using G mapping for this, but there's also Hector. There's actually a bunch of other ones, excuse me. And so the published map ODOM transform is, or the TF map scan match transform frame name, that has everything to do with how Hector is going to interpret and work on its results.
And what's Hector again?
Hector is a different version of Slam. So in order to go ahead and take a look at which one you'd want to use, you're going to go to ros.wiki.org, and you're going to go ahead and type in Slam at the top here.
And there's Hector Slam.
And you're going to find the main usages of Slam, but these are mostly the top two here are mostly for LiDAR, for discrete plane.
Oh, gotcha.
There's also RTAB map, which is down here, and that's using for RGB. D-Slam, which is using a camera with some sort of depth semblance, or two stereo cameras. And so they have all these different types based on the system that you're working on, cartographer as well. And so you get to pick which one you want to use based on the system that you're trying to work with.
And if there's a package out there that already does what you need, just go ahead and use it. Don't recreate the wheel.
So for most of the systems that I built is we've started all open source, and then we found blocking parts of our system or different use cases that we need to address, and we'd start slowly either replacing or adding on or working with those current systems.
So for your folks that are watching in the audience, these RoboMaker guys have been helping with the acceleration as well of ROS 2, correct? So that's kind of what he's referring to now, those moments when they're like, hey, you know what, let's add this or improve this and stuff like that.
Yeah. And so that'll be Robot 1. So Turtlebot 1 just needs to be able to move around and then add G mapping. So add a version of Slam so that it knows where it is. And there's a couple things I'm skipping over here, but G mapping will work on that as well, which is something like state estimation, where you want to use G mapping will end up doing it for you, but it allows you to merge your sensors intelligently, because if you just take your sensors for their word, they may be wrong. And it's easier to start using the dynamics of your system and some of the error in your system to help you calculate that forward.
Sounds like sensors aren't fully trustworthy.
Not always, no. I don't always trust my eyes, so or when I fall
true.
downstairs. So
Something fell in those moments.
Right. And so for Turtlebot 2, we're going to do the exact same thing. We're going to say, hey, there's Turtlebot 2. We're going to put a new namespace in here. But one thing that we didn't do for Turtlebot 1 that we are doing for Turtlebot 2 is we're remapping the map from Turtlebot 1 that's generated from its SLAM to go to Turtlebot 2. What this allows us to do is all we're doing is taking the data that comes out of Turtlebot 1, putting it to Turtlebot 2 for the map. So that's all we're doing there. The next thing we're going to do, exact same thing, we're going to launch Move Base. We're going to use Turtlebot 2 instead of Turtlebot 1. And then we're going to use AMCL. Now, I did not handpick all of these, no matter how much I want you to think that I know that much about AMCL. But all of these we're actually taking out of the Turtlebot 3 navigation stack as well.
So it just comes as the default ideas, suggestions.
Exactly. It's default suggestions, and you can start changing them. I actually have changed a few of them for the purpose of this demo in order to allow us to visualize a little bit better and also not crush my machine with processing power.
That's important.
And then, so the other thing that we have here is the initial pose X and the initial pose Y. So if you do not put these in, which is fine, because the nature of AMCLs we'll see in just a minute is it allows you to do global localization in a very interesting and cool way. But if you do put them in, it makes your life significantly easier if you know where you start. And we'll go over that kidnap robot problem in a minute. And so that's all I actually have here. And finally, the last 4 pieces of this is just making sure that the IDs and the topics that AMCL are listening to are prefixed with Turtlebot 2.
Okay.
And that's it. So that's all we have in this this launch file. And so let's go ahead and start, let's compile and then go ahead and launch this system up.
All right.
And let's see what we can get going. So let's do Qualcomm build. We go ahead and build that one. And let's launch. Here we go, right? So let's launch that simulation. And I'm just going to let that come up just really quickly so that we're confirmed. Okay, here we are.
The suspense is killing me.
I know. We're missing a client right now, so we'll find out in a minute.
Are we waiting 10 seconds? No.
We might be. MultiRobot Simulation. So that should have launched that. So let's just double check it. Just gonna bring that down real quick. Lucky thing about live coding. So let's just launch that again.
It's always fun to have to troubleshoot when you're live.
I know, right?
That's why I don't really do live internet demos at major talks. I just realized that's not worth it.
So robot 1 should be here, but maybe I don't have the client running right now. And I think that might have just been it. And it was it, so that was my mistake.
Oh, nice.
So 2 robots, happy days. And let's take a look and let's launch this and make sure that we configured this properly. So we're going to do ROS launch. We're going to do MultiRobot Simulation again, or MultiRobot in this case. And then we're going to want to launch the MultiRobot navigation stack. And hopefully no errors. No errors, just a lot of logging. Awesome. And finally, let's go ahead and bring up our tool page. Let's bring up RViz.
I love RViz.
Boom. Cool. So what do we have now? First, let's go ahead and take a look at RQT and understand that we configured the system properly, because it's the first thing you need to check is, did I configure the system properly? Don't really start moving anything yet. And we're going to have a little bit of a mess now because we've just started doing
some came through.
Yeah, wow. So it's amazing what you can do using some of the open source software out here, and also just help you to understand what's actually happening in your system before you go ahead and create your own and understand what interfaces are the reason why we choose these interfaces. So the first thing we're going to check is, how did all of our system get up and actually make the transforms happen? So let's go take a look at the left. Notice we now have this map, this common map frame that both Turtlebot 1 and 2 are now connected to. And this happened due to AMCL and gmapping using the same frame called map. So AMCL is localizing on map. So notice how we get here. We get AMCL, Turtlebot 2 is localizing there. And if we look over here, Turtlebot 1 is working with gmapping. Sweet.
And does broadcaster mean that this is publishing things versus listening?
Exactly.
Okay.
So these are what's actually publishing these transforms. And what we can see with listening is over here on the right side. So let's go ahead on the right side and see if we can make this a little bit clearer.
Yeah, because this is the one where a lot of the changes really
really occurred. So notice for what we had before, we had these two before. So we had the joint state publishers and the gazebo. And as we move our way on, we can see that now these transforms have now propagated their way from the state publishers into the respective SLAM or in state estimation. So these two are going ahead and deciding where they are based on that map.
Okay.
And this one's actually creating the map. So we'll go ahead, and if we take a look around here, maybe we'll see, we don't get to see the map. I believe one of these is actually publishing the map from gmapping to AMCL. And then finally, we have two identical move bases. So they're both configured identically, and they'll both drive the robot around.
Right.
So you guys have any questions on some of this situation that we have going on here?
How do you kind of even begin? I mean,
So,
left to right, right to left.
It's a little bit tough. Since it's a closed loop system, you're going to have a left to right and right to left component. So it's going to look kind of like a circle. And while it doesn't look like a circle directly here, you can kind of follow this. So you have the TF frames being published, which then goes to AMCL, which then moves to move base, which then publishes the velocity that we want to have back to gazebo.
Yeah, so all the new additions to the graph make sense. And I guess initially the first thing that hits me is, oh my goodness, how do I make sense of all these arrows that are going both ways?
Yeah.
But now that makes a lot more sense.
Yeah, it can get a little bit difficult as you keep going, and that's where namespacing and grouping really comes in handy. What I would do from here on out is start grouping pieces together into localization. Right now there's only AMCL and gmapping, but maybe you have a robot that also needs a separate state estimator that goes on top of AMCL with different types of sensors. Such as maybe using the IMU, which AMCL or gmapping may not be using at this current moment. Unsure. I don't know if I configured it. If that were the case, I would then want to group those into SLAM or MoveBase.
Okay.
So that'll be running there now.
It looks like we might have a question from the audience, actually.
Sure.
All right.
Oh, yeah. Somebody asked, anyway, go back for 1 second. So, Channel asked where can we get the robot? Does this robot actually exist?
This robot does actually exist. And
It does actually exist.
And it's by Robotics. And so they're actually building the Turtlebot 3. And so you can actually buy this robot, and all of these packages are provided from them, or some of these packages are provided from them, and coordinated with other open source packages, then we can actually make this system work.
Do we have a good link that we can shoot in the chat for them?
I actually did just shoot a link in the chat for people.
Awesome.
So it's there.
Yeah.
Thank you so much for that question. We do get that a lot every time we have a talk related to RoboMaker in these past few months. Or at least one person will go, okay, cool, but what kind of hardware? Or does it really matter? Do I actually need hardware? Where does that happen? Do you sell the hardware? So yeah, we get this a lot.
And also some of these platforms like that are really, really nice when you want to go ahead and start learning and experimenting with robotics, but it's also really nice just if you are a PhD working in or even just a hobbyist that wants to really work into some of the math behind MoveBase or any of the localization, you can actually just replace it with your own and do a bunch of research and try your own algorithms in simulation and in the real world. It's just fantastic.
And the nice thing about that is that if you don't know if you want to right now go ahead and spend money on hardware, because maybe it's not an investment that you can do if you're an individual hobbyist or if you're from a school and there's a lot of students to account for, you don't have to rush off and buy hardware right away. You can actually do pretty much all of this, as you saw, just testing and running your code in simulation. Mm-hmm. So you still get to learn, and you don't have to be blocked merely because you don't have hardware right now.
Right. One thing you will find is that this will not work exactly as it does in simulation as it will in hardware. There will be changes and other issues that you'll encounter as you keep going. That's part of the fun of robotics. It never really ends. You'll always find a new problem. You'll always find something that works differently in simulation than on your robot.
What's one example that you encountered where this looked great in simulation, but god damn it, every time I actually deploy this to my robot, something goes haywire?
Yeah, one of the biggest things is actually measuring and understanding where all your sensors are in relation to the center of your robot. Now, the TurtleBot has it all done for you, but when you have a real robot that you're building, you're going to have to do all that measurement, all that fusion, make sure that there's going to be like little errors in each of them when added together are catastrophic. And so as you continually build your own robots, you'll start learning that you need these sensor initialization functions that try to go ahead and figure out where they all are based on what they're seeing. So maybe a calibration, and you're going to go ahead and put like a bunch of screens around your robot, have it turn around, and then do some measurements and start building its own config file. And it's just a lot. It's really cool.
Well, I'm just getting into it just recently myself, as I've mentioned already before in previous episodes, and I'm really enjoying it.
So our next piece, though, is actually getting these robots to move. So now that we have the robots in here, we actually have everything we need in order to get them to move. So
now we can actually drive them to the same place on the map and see if it worked.
Well, so almost. Very close, yes.
Oh, no. What did I say wrong?
No, you're great.
What was the right way to say it?
No, that's perfect. Almost as in we're not quite ready for that. We're actually missing one or two things.
Okay.
So let's take a look at these two robots. Let's see if this looks anything like what we see here. It kind of looks like it. So here we have the two robots next to each other. We see a couch and we see a couple other pieces of the system.
I feel like a dude designed this world because there's like no decorations and then like a bar lifting and stuff. I'm like, oh god.
Yeah.
It's a dude's apartment, right?
Luckily mine was not configured by me, so it's very nice. So here we see the barbell here. It doesn't look like a barbell.
How do you know that's a barbell?
Exactly. So how do you know? How does the robot know what that is? And in this case, they don't. That's why we're using some of these lighter sensors, which are like LiDAR, that only see in that plane. So they don't see that bar. They don't see a lot of the features that you and I see in the world. And so it actually causes a lot of challenges for them, as one could imagine. So we see the two robots there. They're in the right position. Let's try to get one to move. So the first thing I'm going to do is use something called topic tools. So first thing is I'm going to do ROS topic list, and I'm going to list a whole bunch of these topics. Now this is all those lines that we saw in the RQT graph. This is just them listed out. The one thing I do know that you may not if you're coming new to this 2D nav goal gets published to a very specific topic, and I know that topic, if I do ROS topic list and I grep for simple, I know that we're going to have two here. We're going to have this move-based simple goal, and that's the goal that's coming from Arbas. And then I have these two other goals that are two listening to it. So the TurtleBot 1 is listening and TurtleBot 2 is listening. So let's get TurtleBot 1 fired up. So we're going to do ROS Ross run, topic tools. We're going to go ahead and relay. We're going to relay from this one to this one, if I remember correctly. So it's robot 1 to 2. Let's go ahead and publish and try to get this robot. There we go. We got the robot driving.
Oh,
Nice.
All right, so robot 1 is now driving around the system, and I just gave it a manual goal. The cool thing about person detection is that it has its own route set up so that the robot will drive around and use its camera to look at the walls. Well, now, if you wanted to, you could have the two robots drive reverse routes and look at the walls and try to do their own system and maybe have coordinated efforts. This project actually came from a little hackathon where we were trying to do exactly that. And so it was pretty fun to end up implementing that way.
How many hours did it take you to put this hackathon project together, and how many folks were involved with you in this project?
That's a good question. So this part of the project was more of a stretch goal. We actually had quite a bit else. So this took me a little bit while just to get it working right with the packages that I selected. But we actually worked on a lot of different pieces of it. So it was 3 different people, and we worked on, first of all, making a Nerf system so that
Nerf system?
we put the
oh God, can I change teams? Okay. Just
so
kidding.
we put a an automated Nerf gun on top of the one of the turtle bots, and then we had one of the other turtle bots go out and try to scout. We managed to not get both of those done because it was a one-day hackathon. And we did get the turret working and that robot working, but we never got to this system. So just wanted to make sure and see if we could make this happen. And we realized that there are quite a few people that could really benefit from understanding what these robots are doing. So right now this robot is driving around. Now remember, Turtlebot 1 is using G mapping right now, so it's the one doing its slam and its
we can actually see the wheels rotating, can't we?
We can, yeah. So we can see the wheels rotating right here. We can also see it kind of going off skelter a little bit. See how it keeps jumping around a little bit? And that's G mapping trying to reconfigure for where it is and what it's seeing. So there's always going to be this little bit of jitter, especially when you have low quality sensors. So and quality,
we have low quality sensors
we do,
today.
and that's okay. It all depends on the use case that you're trying to do. You don't need, if you're driving a little robot puck around that just needs to go ahead and get under things or just around a very basic layout that's like 2D and you're not going up any stairs or in any elevators or anything, even that.
Maybe like an iRoomba?
Yeah, maybe something like that. You don't really need amazing sensors in order to do that. So as we look around, we know that this robot has started to figure out where it is. We're going to have a couple more things. We're just going to fill out this area as it goes ahead and drives around, and then we're going to get robot 2 working.
And I think now that it's been mapping out its environment, I'm starting to understand better and think, oh, wait a minute, that must be the sofa, right? In the middle. Okay, gotcha.
So what I'm going to do real quick is I'm going to send this robot to the kitchen. So that I can go ahead and map on over here, and just because I know it's here. Now there are other packages that you guys can use. There's Exploration Lite and all these really cool packages that allow the robot to do this automatically. And I'm just doing it manually just so you can see a couple different pieces of it.
So it looks like we got another question from the chat. And it looks like the username is Cheng Hong GM. Let's hope that I said that right. This person is wondering, what is the green line doing?
Oh, that's a great question. So
we keep using the green line, the little arrow, but we haven't actually said what it is.
So let's actually dive right into that. So there's a couple different pieces. So the green arrow is coming from MoveBase, and that's using a couple different motion planners, 2 different motion planning algorithms. One is for global motion planning, and one is for local motion planning. We have to differentiate between the two in this instance because we'll get to that in just a second. So how this works is it's using the map. The Turtlebot 1 is using the map to go ahead and build a model in its head about where it's allowed to go. And this robot can't fit everywhere. Notice that some of these, if we look over here, are a little bit too close together maybe for that robot to get in there. Let's take a look at what that is real quick. Maybe we'll make some semblance of it. Oh, it looks like chair legs.
Let's do the chair legs.
So we have some chair legs over here that maybe the robot can't get under or can get under. But how do we know that? Or how do we figure out and code that? So we actually build this thing called a cost map. And this is a very pretty cost map. And if you look right in the center here, these are areas, the pink is where the robot cannot possibly get to. They are isolated. They are inside of walls. That is impossible to
How
get
do you
to.
know the color scheme? Is there documentation on this?
There is some documentation on the color scheme, and it will, if you go to ross.org, you'll see that.
Okay.
The next thing you see is the cyan color, and those are a definite no-go. So that's like something that I measured was a wall.
Oh, okay. So maybe like this is the outline of the chair leg.
Exactly.
It definitely cannot transverse okay.
Right.
So
The pink is the no-go area. The cyans definitely can't go, and then there's this like kind of faded piece coming out of here. So if we look at this faded, what it's actually doing is we're trying to push the robot away from obstacles. So now, if you are walking in a hallway, do you walk really close to the wall? Do you tend to walk towards the middle? Now, these are all preferences that we have as people. But when we go ahead,
how dirty the wall is.
Yeah, or how close you want to get to a chair when you're wandering around here. And so, because we all have preferences, we learn these preferences. We actually just code these into the robot. We have this code saying, hey, let's take a look at this map, and we're going to build a cost map. We have these rules that say, well, you can't hit walls, and we have to blow it up the size of the robots. This way, we can say, well, the robot is just a point, and so we can expand all of our obstacles by the size of the robot so that we don't hit them, or half the size.
Okay.
And then what we do is we build an algorithm that just says, well, anything that's that close to the wall should probably not get near. So let's give it a degrading function that says, hey, this is a 100% no-go, and then as you get a little farther away, that's like a 97% no-go, and then we keep going until it's like, okay, 0%, you're free.
So it's actually managed by percentages?
It's managed by a cost map between 0 and 255.
Okay.
Yeah.
Interesting.
And so,
what about the blue? Is that okay area?
the blue is areas that it would preferably not go. So it still has some cost, some non-zero costing, like 10%. Please don't go here. And we can see that as we start to try and navigate this robot around. Let's actually bring it right through one of the blue areas. So if we bring it right here, what we expect to happen is it to look like a valley. So if we look at this as if it's topological, and the green line is trying to find its best way through this, it's going to try to find its way to the middle of the valley. And so let's watch this green line make its way. Notice how it's going to go ahead right down the center of this valley, and see how it's curving a little bit away from this obstacle, trying to stay right in between those two obstacles. And so that's how this algorithm works. It's using something called A-star to find the shortest path with the least cost.
Okay, that makes sense.
Wow, that's cool. Yeah.
Yeah.
It's very cool. And
Can't
so
stop looking at it.
there's one other piece to this when this is working. So that was the global planner. Let's send it on over here and take a look at some of the local planners. Notice how it skirts the outside of this blue, because that's the fastest pass with the least cost. So we're going to add one more piece, and this is called DWA. So I'm actually going to remove these transforms real quick. You're just going to see the lines of where the robot is going. This is the local trajectory planner. So we have this global planner, which allows us to not hit anything, which is this green line. What the purple lines are doing are trying to follow that green line. So the robot's not perfect. You send a command to the robot's wheels, and it may be just a little bit off, and that's okay. And the simulator actually handles that. And so in order for the robot to try and stay online, we have to do these small local plans to try and get on that line. And what it's doing is it's fanning out saying, okay, here's 10 different options, or 100, or whatever, however many options of possible trajectories I can do. What is my optimal one to get back on that line? So that's what move base is actually doing. So let's go back to the TF. I'm not really sure quite where it's going. We decided.
Can I make it?
Yeah, I just kind of decided.
Oh, he's going
Hey, little
right.
guy.
Oh, there we go.
Oh,
Okay, it's
right.
going backward. Okay, so.
It is being a good robot. Okay.
So there's some play in the system. So now let's take a look at Robot 2. Now Robot 2 and AMCL. So AMCL is the Adaptive Monte Carlo localization method. And so what it's doing is it's pretending that there are a bunch of different robots around it, all with slightly different angles and slightly different dynamics, slightly different movements, and all facing in a little bit different directions. And then it's assessing the probability that it's in one of those locations based on what it sees. Okay. And so what we tend to look at and pretend they are is little fish.
A little fish.
Little fish. So let's go ahead and take a look at this. Now, we're going to go ahead and here. Look, we have an arrow right here that's just a straight arrow. So there's no little fish in this one right now. So let's get these robots actually moving. So I'm going to go ahead and stop relaying TurtleBot 1, and we're going to go ahead and relay TurtleBot 2. So we're going to do ROS, there we go, ROS, run, topic tools, relay, and we're going to go ahead and relay to TurtleBot 2. So we're going to do /move base simple /goal to TurtleBot 2. Hopefully I did that right. Let's go ahead and get this robot moving. I'm going to go ahead and move it over to here. Oh, I need to do it twice because of a little, I may have done that a little bit wrong. Let's find out.
So this is another good example of just seeing how sometimes fiddling around with the simulation can be a little bit hectic.
Oh yeah,
It doesn't
so
always just innately
work, right. One thing that's happening here is that the other robot actually saw this robot. So it might actually be sitting on a no-go zone. It is sitting on a no-go zone.
Oh.
So the robot has localized itself. Notice you see all these robots, but it can barely, it's trying to move. Oh, it finally moved out of it. It had a little bit of an escape attempt. And notice how the robot's kind of like drifting around a little bit. It's pretty confused, doesn't really quite know where it is, and now we're finally a little bit back on top of it.
Okay.
And so the robot's kind of freaking out a little bit as it tries to get off of this spot. But notice how you see all these little arrows, right? Look at all these little arrows kind of flowing its way. So every time that the robot moves, all of these arrows advance one step.
And there's not just one big arrow, there's several.
There's several.
Now that we're
There's
zoomed
tons
in.
of arrows,
Why
right.
are there so many arrows?
So there are tons of arrows. Oh, and it might actually be colliding with the barbell at this moment.
Oh no.
So
Oh, that is the barbell.
it did. It made it way under
Did
it.
it
make it there? Oh,
Let's
no.
find out. Where is said robot? Oh, actually, the robot does no idea where it is. It actually drove way over here.
Oh no.
I know, right? So it's really confused right now. And so it might have messed up mainly because, let me go back. Mainly because it was on top of that little spot earlier, and it really doesn't understand where it's going.
Oh,
So-
it's actually in a spot that's not really been mapped at this
Yeah,
point.
it's
over there.
way over here. So let's take a look at what's going on. It's right here.
Oh,
Okay,
no,
cool.
no.
So let's do something called the kidnap robot problem. So the robot is
Kidnap a robot
the
problem.
kidnap robot problem.
Okay, this
we're-
is legal, I promise.
So we're at a point where our localization has failed us in this simulation. So the robot's here. It thinks it's here. It's actually getting there, getting closer to where it actually is, and it might actually get there. But for the sake of exciting and changing how this is working, let's pretend that it actually is going to get there. Okay. Well, before it gets there, let's explode all of these arrows all across the screen in order so that we can solve the kidnap robot problem. What we're going to do is we're going to take all of these AMCL particles and disperse them equally throughout the map. And then we're going to take a sample with our scanner, and from each perspective, we're going to decide whether or not that robot is more probable that we're in that location. Okay. And then we're going to do that over and over and over again. And now as they become less probable, we're going to delete those arrows because they're probably not it. And we're going to respawn them in a wave or an area around more probable particles. Did the robot actually figure out where it was? It did not. It is somewhere over there next to...
Right next to the other side of the wall.
So it's right here. The robot thinks it's here. This is a perfect simulation to figure out what's going on. So let's go ahead and do one other thing. So let's take a look at what AMCL is. So ROS node list. We're going to see a bunch of nodes that we have. We're going to see AMCL here. So we're going to do ROS node info on the AMCL. And we're going to go ahead up and we're going to see some services here. Now there's this global localization service. And if you go to ros.org, you'll see that AMCL has all these services published and they can explain what they're doing. What this is going to do is do a global localization. It says, I don't know where I am. I give up. Let's go ahead and restart. Let's refigure this out. So we're going to do ROS service call. We're going to call this service. And I'm just going to tab through because it's going to automatically do this for me and hit enter. And let's go ahead and take a look at Arvis.
Oh,
whoa! All of
you
these.
really did distribute them
Right.
everywhere.
So we just distributed all of these everywhere. And the robot's going to go ahead and try to reorganize where it is. Now it keeps, it's trying to organize up here as to where it was prior. And that might be due to some inconsistency or some inability to see something really, really nice over here. So I'm going to start moving the robot. And the reason why moving the robot's really nice and gets it to work is because when the robot is moving, it's moving all the particles as well. And so you have more of a chance of those particles maybe hitting a wall or being in a place that are not optimal, and they get deleted. And so we can take better samplers. Notice that the robot is still going over here, and we have the robot somewhere else. Oh, there it is.
It's getting closer.
And notice that these might start migrating towards where the robot actually is, which is somewhere over here. So let's see if that ever ends up getting there. Maybe. We'll find out.
Maybe we stay on the stream for another hour.
Yeah, maybe we do that.
No, don't worry.
And so we did this kind of on purpose in that this is a very naive way to have the two robots know about each other. One is publishing the map to the other. And a couple of the reasons is that the other robot sees this current robot. So there are other ways to make this work a little bit better, but also that because of that robot seeing the other one, you'll get black in your map because the black is just saying, hey, I saw something here. It doesn't recognize that it's the other robot. And the other robot's like, no, I was here. And it thinks that it's inside of an obstacle now. So you have all these problems that you have to add. And so we add new nodes that do something like situational awareness, like based on the situation, based on what I'm receiving, is this correct? And can we delete anything or add anything to the map to make ourselves understand what's going on? And finally, let's make the two robots at least try to drive together. The other robot does not know where it is, but we can use one of the robots to discover where it is by going ahead and doing ROS run or relay. And we're going to relay the first one, and we're going to go ahead and move all the robots over this way. Let's get it. Yep, so we're going to have robot 1 and robot 2. This robot's a little bit confused, so at that moment, we'll go ahead and scatter those particles one more time. Global localization, scatter, and hopefully we'll see these scatter in just a moment. One more time.
Here we go.
Nice.
Yeah. Cool. It thinks it's inside the couch right now, so
Yeah.
that'll be
Thanks, it's
that'll be
underneath.
interesting. When it really is over here. Now, the issue is that the couch is really full of features. It's really nice because there's a lot of different features around, a lot of different obstacles around it. So it makes matching a lot easier to match on that location. And that's why we're getting this cluster around the center of this table.
I didn't realize that there were so many features just into the couch.
Yeah. So because the couch is this L shape and has very dark features, a lot of the scans that are matching would actually match to that couch. So these are different things that you need to worry about when you're actually building your system.
So if our Turtlebot 1 goes and actually maps that area where our robot is currently lost, will that actually help our robot?
Yeah, it will help a little bit, but remember that since the robot will be in that location and will also be seen by this robot, you may see some issues where it doesn't fully understand exactly where it is. But we'll send robot 1 over there anyways to scout the area.
Nice.
Well, I think we still learned a lot, right?
Yeah.
It was still really great. We still got to understand better about how to create different relationships among robots. We learned about launching multiple robots inside Gazebo Simulation. We learned about transforms, right? We also learned about namespacing. We learned about how to configure SLAM and other things related to localization. And we also learned about adding a path planner to different robots and how to set their goals using the RViz ROS visualizer tool. So we're hoping to do a lot more RoboMaker episodes, so stay tuned for that, and we'll have some more coming up, probably a voice demo one. But thank you so much for tuning in today, and Cameron, Ross, thank you so much for joining us and for making it so much fun.
Thank you.
Thanks for joining us.
All right,
Thanks, guys.
have a good day.